Today we're doing a discrete mathematics and its applications problem by Rosen, chapter 5.1, question 10. The question gives us a sum, 1 over 1 times 2 plus 1 over 2 times 3 plus dot, 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 plus 1 over n times n plus 1. And it wants us to come up with a closed form or a formula that will equal the sum to some number n, where n is an integer. And then it wants us to prove that what we come up with is correct. And it says that we should do so by examining small values of n in the expression. So this could be a little bit longer video than normal because we want to take our time here and make sure that the conjecture is something that will be correct and we don't end up proving something that's incorrect. So for n is 1, we have 1 over 1 times 2, or 1/2. Essentially, it's the first term. It's just 1/2. Now, n equals 2 means that we're taking the first term, and we're going to add the second term, and that is 2 times 3. So that is 1/2 plus 1/6, which, if we are thorough, will be 3/6 plus 1/6, which will be 4/6. 4/6 will reduce. I think it'll be easy for us in the conjecture part if we have something reduced. So 2 goes into 4 2 times, 2 goes into 6 3 times. Let's do a couple more. So n equals 3. Now we know that's the third term summation, so we are adding another term, which will be, in the case 3, it's n, so 3 times n plus 1, which is 4. Now we know this is 1/2 plus 1/6 plus 1/12. So that will equal, and we will get like terms. So to get 12 on the denominator, we're going to multiply the first term top and bottom by 6, so we get 6/12. The second term, we need to multiply top and bottom by 2, so we get 2/12. And then we can leave the second, or the last term, alone. And that's 6 7 8 9/12, which reduces. 3 goes into 9 3 times. 3 goes into 12 4 times. So let's look at n equals 4. So that's 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5. Again, it's the fourth term, and the formula is multiplying consecutive integers, 1 times 2, 2 times 3, 3 times 4, 4 times 5. Again, n times n plus 1. So we know this is 1/2 plus 1/6 plus 1/12 plus 1/20. All right, so now we get common denominator here. Let's do this. We know that the sum of this from before is 3/4. And then we'll add that to 1/20. So this becomes 15/20 if we multiply the top and bottom by 5, plus 1/20, which will be 16/20. 16/20 will reduce if we have divisible by 4. 16 is 4, divisible by 4/20 is 5, so that's 4/5. All right, so let's look at what we have so far. We did for n values 1, 2, 3, and 4. So let's take a look at the pattern of the reduced form. So we had 1/2 was the first, 2/3 was the second. So this is for values of n. This is 1, 2, n equals 3 was 3/4. And then we had 4/5 for the fourth term. And we're expecting the pattern to continue. You could do n equals 5, 6, 7, 8 if you're not convinced of this. But now our conjecture looks fairly straightforward if we look at what's happening to the fraction. 1 over 2, 2 over 3, 3 over 4, 4 over 5. So what's happening, it looks like if we start with n, because remember the first term is n, that will be the numerator. We'll have 1, 2, 3, and 4. And the denominator is 1 more than the numerator, right? Because 2 is n plus 1, 3 is n plus 1 when n is 2, and so on. So this will be our conjecture. We will say our formula of 1 over 1 times 2 plus 1 over 2 times 3 plus ... plus 1 over n times n plus 1 is equal to n over n plus 1. So this is our conjecture, which we will have to prove. A lot of cases when we're trying to find a closed form of a summation, it helps to look at the first handful of terms, which we did here. Sometimes it's not advantageous to reduce them. For us, it gave us a clearer picture of what the pattern was. Sometimes it's easier to look at the unreduced form because sometimes you'll sense there's some multiplication or factorial or something else of use that we can conjecture. So here's our conjecture. We want to prove this. So we're going to do this by induction on n. N here is going to be all values of n is greater than or equal to 1. That's our conjecture. We should have said that here. We could also have said for positive integers. All right, so induction requires us to do a base case. So we'll say the base is n equals 1. And the left-hand side, again, we know what that is. That's the first term. It's 1 over 1 times 2, which is 1/2. We could also have looked at this form here. If I plug in 1 for this, I get 1 plus 1, 1 over 2, 1/2. So either way, the left-hand side is equal to 1/2. Now our conjecture is the right-hand side should equal 1/2. So the right-hand side is 1 over 1 plus 1, which is 1/2. So that indeed holds. So the base case holds. Now for the induction step, the inductive step, we're going to conjecture. We're going to assume an induction hypothesis. We're going to assume that our formula is true for all values of k greater than or equal to 1. So this is our induction hypothesis. So I'm going to label this the induction hypothesis. I sometimes use this, I sometimes don't. Longer proofs, when I'm tired of writing, I write IH, and so I'm say by IH, I don't have to write induction hypothesis, but this I don't think will be very long. So let's just write it out. So we want to show now that the next case is true. If we assume this conjecture is true up until some k, we want to show that it will hold for every k value after k, so k plus 1 in this case. So the k plus 1 case is true. This is a heart of induction. It's assuming if, like a series of dominoes, if you pick any point along the domino chain, if the dominoes fall to that point, then I'm saying it's going to fall past that point. So if this is true up until k of 6, then we're going to show that's true of 7. So no matter what k you pick, I've already proven that the next step is true. So it would be impossible to find a integer that is true and where the next one isn't. That's why we show the k plus 1 case. What we're going to do is write down the k plus 1 case on the left-hand side and the right-hand side. So we should think of this as being the next term. So we know that this is true up until k plus 1 times k. Now I'm going to replace k with k plus 1. So this becomes k plus 1. This becomes k plus 1 plus 1. And we're hoping this is equal to, put a little question mark because we're not sure. This is what we're trying to prove. So it would be wrong to say that this is equal. Now I'm going to replace the k over k plus 1 with k plus 1 over k plus 1 plus 1. This is a little ugly, so I'm going to simplify it so it makes a little bit more sense. And you'll see that this term on the left is just the next term. This is k plus 1, k plus 2, which would make sense because these are consecutive integers being multiplied. And we're wanting to show that this is true for k plus 1 over k plus 2. All right, so algebraically, if we could show that one of these sides, the left-hand side or the right-hand side, are equal to the other, then we have proven that this is true. In most cases, with proofs like this, with summations equal some closed form, you begin with this summation side. I just think it's easier to replace the induction hypothesis. So in other words, we're going to make the left-hand side look like the right-hand side. So our left-hand side, again, I'm just going to rewrite it, is 1 over 1 times 2 plus 1 over 2 times 3 plus dot, dot, dot. 1 over k plus 1 plus 1 over k plus 1 times k plus 2. The dot, 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 usually 3 dots denotes that there are an undetermined number of terms between the two plus symbols. It's just standard, 3 dots. All right, so the first thing we're going to do is we're just going to group the first k terms. And the reason we're grouping the first k terms is because we have an induction hypothesis. Induction proofs, we will always use the induction hypothesis. I always say that if you do not use the induction hypothesis, that you most likely did something wrong, even if your answer is true. You made assumptions you shouldn't have, or possibly in your proof, you use the induction hypothesis without quite realizing it. I like to be more explicit when I'm using it. That way, if I mess up somewhere along the lines that my proof is wrong, I can see at the point at which I assumed something was true and then work from that point. So again, in the brackets is the induction hypothesis. We said that was true by assumption to k over k plus 1. So simply we're going to substitute what that equals to. And then we're going to keep this term here. We're just going to tack it on here. We're going to say this is true by the induction hypothesis, RIH. All right, so now if I can manipulate this to look like the right-hand side, algebraically manipulate, then we will proven that the left-hand side and right-hand side are equal. And then our conjecture is true, and we've found a closed form for that summation. All right, so I really want to add these two. So like terms, the denominator of the left term is just k plus 1. The denominator of the right-hand term is k plus 1 times k plus 2. So I need to multiply the first term, top and bottom, by k plus 2 if I want to add these two, which I do. Now, you don't really need to do this intermediate step here. I just want to make sure it's clear that I'm multiplying the first term by k plus 2 over k plus 2, which is just 1, right? If I divide those, it's 1. So then I get k plus 2 times k plus 1, and then the common denominator is k plus 1 over k plus 2. All right, so far so good. Why don't we multiply out the top In other words, we distribute this k. So k times k is k squared. K times 2 is 2k. And then we have this 1. And then at the bottom, we have k plus 1 over k plus 2. Now let's factor the top. I know we distributed, that's to multiply and combine the terms, and now we're going to factor. So a quadratic will factor, hopefully, into two binomials. So here we have two numbers that multiply that give me 1, that when I add them give me 2. The only real possibility here is 1. And so we get k plus 1 times k plus 1. And I'm going to bring the denominator back in. And now we see we can cancel something. We have a k plus 1 down here and a k plus 1 up here. And then once we do that, we're left with k plus 1 over k plus 2. So algebraically, we've shown that this is equal to k plus 1 and k plus 2, which is what we wanted to show. Here's the question mark. We wanted to equal k plus 1, k plus 2, which it does. So we've shown that this is equal to the right-hand side. And thus our conjecture that 1 times 2 plus over 1 over 2 times 3 plus dot, 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 plus 1 over k times k plus 1 is indeed equal to k times k plus 1. So this is true. We can put a little box or QED. In any event, we are done. If you want to see any other videos from this book, say so in the comments. And if you subscribe and do all that stuff, I'd appreciate it. Thank you.